Okay, these are the rails that we mount a modern solar system on. We use a pair of rails and then we bridge the solar panels over them. On the rails, we use top clamps to mount the solar panel into the rails. You can see the rail slot on the top there. And this gives you another view of the rail slot. This is an end clamp used at the end of a row of solar panels. This, on the other hand, is a mid clamp used to bridge between two adjacent solar panels. These clamps are held in place using a T-bolt. You'll notice that the end of the T-bolt is just that. It's a slotted bolt head and it fits into the rail slot, half turn, and it locks in the clamp. With that in place, we can move the clamp up, tighten down the hex nut on top, and put a clamp between two solar panels. Okay, where we start to get into trouble is when we splice together a lot of rails over a long distance. The expansion coefficient of aluminum is one of the highest of all materials. A 100-foot stick of aluminum will expand from below freezing to 100 degrees Fahrenheit, almost 2 inches. The strength of thermal expansion and contraction is so severe that it will take a 4-inch lag bolt holding down a solar PV system, and it can literally bend the lag bolt. The thermal expansion and contraction on a mounted rail can be so severe that it will start to tear the lag bolt right out of the roof deck. In a system with a limited number of panels, we can join the rails with something called a rail splice, shown here. Just as when they're building a bridge, for example, they place an expansion joint. We can place an expansion joint in the rail, substituting this joint for a joint that looks like this. And this joint actually has two fixed nuts and two nylock nuts. The nylock nuts can be tightened down with no danger of them coming apart, loosening up over time, but they can be tightened to allow the rail to move where the nylocks are. Okay, here we have inserted an expansion joint in our rail system. And you'll notice that we have left a gap. And here we have two fixed nuts, firmly tightened. And here we have the two nylocks, and they will allow the rails to expand and contract with temperature. Temperature goes up, the gap closes, the temperature goes down, and the gap increases. So the use of an expansion joint even is not unknown, and if you happen to mount a solar panel next to an expansion joint, And that's the last panel in that row. That's all right. Where we get into trouble is if the solar panel ends in a place that bridges an expansion joint. If we put a clamp out here and we have a whole row of solar panels, the solar panel bridging the expansion joint is going to absorb all the expansion and contraction. And being rigidly clamped down, things happen. For example, a solar panel can break. This is an example of a solar panel that was clamped in a string of panels with no expansion joints. And as you can readily see, the glass in this solar panel shattered. Ideally, we would like some way that we don't have to plan the system so that the solar panel has to end at an expansion joint and then start again. In other words, we need a way to clamp the solar panel over an expansion joint. This is the basis of Sunmoto's new invention. It's a sliding clamp, a sliding thermal clamp. It's specially designed to fit in and be captive in the rail slot so that the panel can be firmly mounted. But what you'll notice here is that there is actually a slightly raised shoulder portion here. So the solar panel fits in here. We tighten the clamp bolt on top. Once the panel's clamped in place firmly, so it's never going to slide up and down laterally, it can still slide back and forth with the solar panel on it. This is a view of the business end of our thermal clamp by making it captive so the solar panel can be torqued down and not fly away, but we still can move. The solar panel is allowed to expand and contract over the rail joint.